Okay, so now let's solve some examples of this Bernoulli equation to see how we can use it, and then I'm going to introduce some alternate forms of Bernoulli equation, and then talking about the stagnation point concept, and further solving more examples of the application of this equation in engineering problems. Okay. So let's get started. So imagine we have something like a building here, okay? And then we want to determine the difference in the pressure between point 1 and 2. Okay, so what are point 1 and point 2? So here we have point 2, and then there is wind that is kind of blowing toward this building. So we have a wind. The wind has the velocity of v1 equals to v naught. This is so point 1, and at point 2 this hits the building, this wind, and then here we have v2, which is equal to 0, right, based on that no slip condition, because this is over the wall of the building, so the velocity of the wind is going to be 0 right at the wall. Okay, so now we want to see if we have this velocity, a wind that is like blowing with velocity v naught, what is going to be the pressure difference between these 2 points? We want to find that. So we can use Bernoulli equation between these 2 points, because why? Because we have we are in a streamline, so we are along a streamline of the flow. This is one streamline of the wind flow. So I can write the pressure, the Bernoulli equation between these two. So for a, and if this flow is steady, means it's not gonna change. It doesn't change. For example, this V1 is not gonna increase or decrease. It's gonna stay the same. For a steady, incompressible, and inviscid, and we assume it's also inviscid flow, we can write the Bernoulli between these 2 points as P1 plus 1/2 of rho V1 square plus rho GZ1 equals to a constant along the streamline, right? So it's gonna equal to the same Bernoulli equation at point 2. So equals to P2, pressure at point 2, plus 1/2 rho V2 square plus rho GZ2. Okay. As you see, because this movement is a horizontal movement, so Z1 and Z2 equal, right, are equal. So this means that these 2 terms are going to cancel out, because Z1 equals to Z2. Okay. So, and also here we know that V2 equals to 0, so I can just write down this as 0. And instead of V1, I can write it as V naught square, right? So this is going to be 1/2 rho V naught square. So the difference between pressure between point 2 and point 1 is going to be as follows. So P2, pressure at point 2 minus pressure at point 1 equals to 1/2 rho V naught square. So this means that the pressure at point 2 is higher than pressure at point 1. Okay? And how much is higher? Is 1/2 rho V naught square. Okay? So the higher the initial velocity, the higher this difference is. Okay? So this was a simple example for using a Bernoulli equation in a kind of applied form. And now I want to discuss and talk about alternate forms of Bernoulli equation. So this is the next topic. The next topic is alternate forms of Bernoulli equation. Okay, so the Bernoulli equation is that we wrote is P plus 1 rho V square plus rho GZ equals to constant along streamline, right? So we can divide the whole Bernoulli equation by rho if rho is constant, and this is one of the conditions that we were able to write Bernoulli equation, the incompressibility assumption. So we can get an alternate form of Bernoulli equation. So P over rho plus V square over 2 plus GZ equals to, again, a constant along the streamline. So this is an alternate form of that equation. And we can even go further and multiply everything by G as well. So we are going to get P over rho G plus V square over 2G plus Z equals to, again, a constant on a streamline. And this is also a form that has a very interesting intuition. And so Z is elevation head. So we call Z as, let me write it down as this. Z here in this equation, we call this as elevation head. So it's the elevation of the streamline that we are investigating. And this kind of shows the potential energy of the particle, right? If you look at from the energy point of view, and we are gonna derive this Bernoulli equation again later using the energy principles, but this is kind of represent the potential energy of the particle, right? So for example, this is the elevation. So if you have a fluid and then you want to release it, say, from a certain height, so this elevation, this Z, is the potential energy of these particles that are in this streamline, right? So this kind of shows the potential energy and represents potential energy in these flows. And then the other one is V squared over 2G, the other term, which is here. So this term, we call it velocity head, and it kind of relates to the kinetic energy, right? So this is the kinetic energy of the particle, okay? And then the last one is P over rho G, which we call as pressure head. So velocity head, elevation head, and pressure head. So these are what we can call from this Bernoulli equation, which is the height needed to produce the pressure P. Okay, so this is kind of the intuition of this Bernoulli equation. So you have like a potential energy. So you have potential energy, sum of the potential energy, and kind of similar like to that, and kind of the kinetic energy, and also the pressure head. So pressure head, elevation head, and velocity head, right? So some of those quantities along the is constant along a streamline in a fluid flow, okay? Also, another way we can say is P is, another way of intuition is static pressure. So if you look at this equation, so P is static pressure. So this equation is for head. All of them are kind of heads. So the first one is pressure head, second one is velocity head, and third one is elevation head. And this equation, all of them are pressure, right? In terms of pressure, as you see, because everything has the unit of pressure. This is pressure, and we can, as one of the first principles we learned in the course, is that you can only sum two quantities which have the same unit. So this has the unit of pressure, so this should have also a unit of pressure, and this should also have a unit of pressure. So the first term we call it static pressure. The second term, rho v square over 2, we call it as dynamic pressure. And then the third term, we call it rho gz as hydrostatic pressure. This was the pressure that we mostly worked in the last chapter, right? So another intuition of an interpretation of Bernoulli equation is as follows, is like the sum of the static pressure, dynamic pressure, and hydrostatic pressure is going to be constant along the streamline in a fluid flow, okay? In an incompressible steady flow. So either you can use any of these interpretations, either the pressure interpretation or the head interpretation. So the sum of the pressure head and velocity head and elevation head is constant along the streamline. Okay? So let me now introduce another concept which is kind of important, and that is called stagnation point. You might hear this when you solve examples or in the literature or even when you look at the book. And now I want to explain what is a stagnation point and what is the pressure, how we can find the pressure of stagnation point. Okay, so let me draw, say, a pipe flow. So say we have a pipe here. And we have two manometers for measuring the pressure. Okay, and we have a velocity profile, a velocity that is in the inlet, an incoming velocity as this. Okay, and then we have at point 1 and point 2 and this is point 1. So the velocity at point 1 is v, and the velocity at point 2 is 0. Say it is kind of stuck here and it cannot go further. So the velocity is 0. And then here we have water that goes up to here, and then we have water that goes up to here. So this has a head of h. And I write this point as point 3 and this point as point 4. So point 3. Okay, so a stagnation point is where velocity is 0. For example, in this example, it's gonna be at point 2 where velocity is 0. So here is a stagnation point, okay? And what we can say by stagnation point using the Bernoulli equation? So using the Bernoulli equation, we can say that here, for example, if we write the Bernoulli between point 1 and 2, we have a streamline here, right? So I can write Bernoulli equation between these 2 points. So P2 plus 1 rho V2 square equals to because it's along a streamline, and gz is z is constant for both of them, right? We have the same z or elevation. I can just neglect that and don't write it down. So it's going to be p1 plus 1 rho 1/2 of rho v1 square, and this is 0, right? Because it is a stagnation point here. So I can say that P2 equals to P plus 1/2 rho V square. Instead of V1, I just write V. And this is the stagnation, we call it stagnation pressure. Okay. So this thing that you see here, okay, is the mechanism that we can find the is kind of the mechanism on periodic tubes that we can find the velocities, right, using these stagnation points. Okay, so if we put something like this, for example, in an airplane, then, and also this one too, and then if we have the pressure difference between these points 1 and 2, then we can get the velocity of the airplane, right? So that's how the velocity of airplanes are also calculated. Okay, so let me write it down. The mechanism of pitted static tubes, for example, in airplanes, to find velocity. So the way we are going to find the velocity in airplanes, and this is the mechanism they use to find their velocity relative to the kind of wind, is they use these periodic tubes, and then you can calculate V from this formula, and it's going to be 2 times P2 minus P one over rho, and P1 is typically the atmospheric pressure, right, at that level. And so you can find a P2. If you get the P2 from this, you can get it from here, from this elevation, and then you can calculate the velocity of airplanes using this formula. Okay, so these periodic tubes are also used in airplanes, and they use the same mechanism like here to calculate the velocity of airplanes. And so this stagnation point has very important implications. Also, for example, if you have a bluff body, any bluff body, say a cylinder or anything, and then the wind is kind of blowing toward this bluff body. Okay, where do you think we call the stagnation point here? Yeah, so the stagnation point is going to be here, right? So if you have a bluff body, the stagnation point is going to be here, right? And so because V here is 0, so it's kind of stagnation point. And you can get the stagnation point based on the velocity, right? If the velocity somewhere is 0, so you will have a stagnation point and also a stagnation pressure. So you can calculate the stagnation pressure of this point using the upstream velocity here, right? So it's going to be the upstream velocity 1 rho v square plus its pressure at that point, okay? And so that will be the pressure, stagnation pressure at this point, okay? And the difference between the pressure between this point and this point, stagnation point, is just 1 rho v square, one half of rho v square, okay? Okay, so now after this, I'm gonna solve some examples, another example of stagnation point, and after that, we're gonna talk about free jets, confined flows, and further solve more examples of these Bernoulli equation in engineering problems. Thank you very much.